Now, let's zoom out to the full picture of all 17 rare earth elements and how analysts should classify them. Rare earths split into two groups based on atomic number. Light rare earths, or LREs, run from lanthanum to samarium, atomic numbers 57 through 62. Heavy rare earths, or HREs, run from europium to lutetium, with atomic number 63 through 71, plus yttrium at atomic number 39, which is classified as a heavy rare earth despite its a lower atomic number because of where it concentrates geologically. The most commercially critical subgroup sits across both categories: neodymium, praseodymium, dysprosium, and terbium, the four magnet rare earths. These four elements drive the majority of commercial value in the entire sector. Everything else is contextually important, but these four are where the investment thesis is concentrated. Understanding the classification matters practically because light and heavy rare earths behave very differently in the market in terms of pricing, geography of supply, ore type, and commercial role. We'll come to that on the next slide. This slide is one of the most important conceptual distinctions in the entire REE sector, and one that trips up many investors who are new to the space. Light rare earths and heavy rare earths are fundamentally different businesses. Light REs, lanthanum through samarium, are found in relatively higher concentrations in the Earth's crust. The main ore types are bastionite and monazite, which are found in large deposits in China's Bayonne Obo, in the US at Mountain Pass, and in Australia. Prices for LREs range from about $5 to 120 per kilogram. This serve high-value commercial roles: catalysts in petroleum refining, glass polishing, and batteries. Heavy REEs, europium through lithium plus yttrium, are found in significantly lower concentrations. Their main ore type is ion adsorption clay, which is highly concentrated in southern China and Myanmar. Prices range from $400 to 3,000 or more per kilogram. They serve high performance applications: EV motors, wind turbines, defense systems, where properties are irreplaceable. Now, here is the more critical commercial problem that every REE project faces, and it's highlighted in the box at the bottom of this slide: the CE and LA problem. Cerium and lanthanum together make up 50 to 60% of most ore bodies by weight, but they sell for only USD 2 to 7 per kilogram. So every ton of valuable NdPr that a mine produces also generates several tons of near worthless cerium and lanthanum. Mines that cannot find buyers for their CE and LA faces serious economic problems because of the cost of process, and the entire ore body must still be paid regardless of whether all products find buyers. This is not a minor operational footnote. It's a structural factor that determines whether many projects are economically viable at all. Of the 17 rare earth elements, 4 carry the vast majority of commercial value, and all 4 are used in permanent magnets, which sit at the heart of every EV motor and wind turbine generator. Let's take a look at each one. Neodymium, at USD 70 to 120 per kilogram, is the primary ingredient in NdFeB magnets. It's the demand anchor for EV and wind applications and the most widely used magnet RE by volume. When people talk about rare earth demand growth, they are largely talking about neodymium. Praseodymium, at USD 70 to 110 per kilogram, works alongside neodymium and is almost always traded commercially as per the NdPr alloy. It is functionally interchangeable with neodymium in most applications, which is why the price tracks closely. Dysprosium, at 1,500 to $3,000 per kilogram, note the order of magnitude price jump, adds heat resistance to the magnet. It is essential for EV motors operating at continuous high temperatures, and its supply is highly concentrated in the southern China and Myanmar. This supply concentration is a significant geopolitical risk. Terbium, at 1,200 to 2,500 per kilogram, it is more efficient than dysprosium per gram. roughly twice as effective, so it's used in smaller quantities. But the market is extremely thin, with severe supply concentration, making it highly sensitive to any supply disruption. The key analytical question on this slide is that a project that produces mainly cerium and lanthanum may look large on paper by volume, but generate very little revenue. The real question and a person must always ask is that how much NdPr does this project actually produce, and does it have a credible plan to monetize its C and LA? This slide introduces perhaps the single most important structural insight about rare earth sector from an investment perspective: the value chain. There are seven distinct stages from raw ore to finished stingered magnet. Let's walk through each of them. Stage 1 is the mining. Ore is extracted from the ground. Then this is the baseline. Value 1 times. Stage 2 is concentration. Flotation and physical processing removes waste rock, producing a concentrate with 40 to 70% total rare earth oxide content. This is worth 3 to 5 times the raw one. Stage 3 is the mixed carbonate. Chemical precipitation at a processing plant produces an intermediate product worth 2 to 3 times the concentrate. Stage 4 is separated rare earth oxide. Solvent extraction separates individual elements at 99% plus purity. This is where things get technically demanding and commercially valuable, worth 4 to 6 times the mixed carbonate. Stage 5 is metal. Chemical reduction converts oxide to metal, a 1.2 to 1.5 times step. Stage 6 is magnets. Stage 7 is Stinger magnet. Power metallurgy produces the finished magnet blocks used in motors and generators, worth 2 to 5 times the alloy. Total value multiplier from raw ore to a finished Stinger magnet is 50 to 200 times. Here is a critical implication. Most of the value is captured at stage 4 through 7, and all of those stages are dominated by China and Japan. A company that only mines and sells concentrate captures less than 15% of the total value created in the chain, which is why we are a REE miner and we are a REE supply chain company are a very different investment proposition. Building on the value chain framework, this slide maps each stage against China's current market share and what that means for analysis. At the mining stage, China controls 60 to 70% of the global output. The insight here is that grade alone does not determine project viability. What the ore contains by element composition matters far more. At the concentration stage, China's share rises to 65 to 70%, and most ex-China miners stop here or at stage 3, mixed carbonate, because they lack the downstream technical capability. At the mixed carbonate stage, China's share is approximately 80%. Some Western projects are targeting this as the initial output stage, which is an improvement on selling raw concentrate. At the separated rare earth oxide stage, with stage 4, China's share jumps to 85 to 90%. This stage requires complex solvent extraction chemistry, and very few non-Chinese operators have this capability. At stages 5, 6, and 7, metal, alloy, and stringent magnet, China's share remains at 85 to 90% throughout. Near zero metal reduction capacity exists outside China and Japan. The key takeaway from this slide is stark. A company that only mines REs and sells concentrate captures the bottom 5 to 15% of the value ladder. True supply chain investment, the kind that addresses Western government security concerns, requires separation and metallization capability. And those things are the stages that China currently controls almost completely. This is a central structural challenge facing every Western RE supply chain initiative. Now let's get into the underlying magnet science, because understanding what makes NdFeB magnet special is essential to understand why rare earth demand is so structurally locked in. The NdFeB magnet was invented in 1982 to 1984, independently and almost simultaneously, by Masato Sagawa at Sumitomo and by General Motor researchers. This wasn't an incremental improvement on existing magnet technology. It created entirely new product categories. Without NdFeB, the modern EV traction motor, the compact hard disk drive, the wind turbine generator as we know it would not exist. Permanent magnets maintain a sustained magnetic field without any external power input. NdFeB magnets achieve energy product values. The headline performance metric of 200 to 400 or more kilojoules per cubic meter, that is approximately 5 to 10 times better than ferrite magnets, which are the cheap, common alternative, and 2 to 3 times better than samarium cobalt magnet. Three parameters define a permanent magnet performance. Remanence (Br) is the residual magnetic flux after the magnet is magnetized. Higher remanence means a smaller, lighter motor for the same output. Coercivity (HCI) measures the resistance to demagnetization by external fields or heat. Higher coercivity is critical for reliability in dynamic high-temperature environments like EV motors and wind turbines. Energy product (BH-max) in total magnetic energy stored per unit volume. This is the primary engineering figure of merit that engineers use when selecting a magnet for a given application. The magnet comparison table on the right summarizes this. NdFeB leads on strength, SmCo leads on temperature resistance, Alnico leads on heat resistance but has lower strength. Ferrite is cheap but weak. For the applications driving REE demand, EV, wind, robotics, NdFeB is the overwhelmingly preferred choice. This slide clarifies the fundamental chemistry that makes rare earth irreplaceable in high-performance permanent magnets, and specifically why dysprosium and terbium cannot simply be engineered out of EV motors. A finished NdFeB magnet is defined by its three performance parameters: remanence, coercivity, and energy product, as we covered on the previous slide. The commercial implications are: higher remanence means a smaller, lighter motor for same power output. Higher coercivity means the magnets survive years of high temperature operation without degrading, and the energy product is the headline number engineers use to specify and select magnets. Inside the magnet, each component plays a distinct role. Neodymium and praseodymium together make up 28 to 32% of the magnet's weight. They create the crystal structure that generates the magnetic field. They are the engine. Boron and iron make up the balance of the weight. They provide structural support and exchange coupling between magnetic domains, essentially the chassis. The dysprosium and terbium together make up 0 to 10% of the weight, depending on the application. They reinforce the grain boundaries to the crystal structure to resist demagnetization at elevated temperature. They are the thermal shield. Here is a critical point highlighted in the heat box problem. An EV traction motor runs continuously at 80 to 120 degrees Celsius. Without dysprosium or terbium, standard NdFeB magnet begins to demagnetize under these conditions, reducing efficiency, generating heat, and shortening the motor's operational life. This is precisely why dysprosium and terbium cannot simply be designed out of high-performance motor applications. The heat problem is not an engineering footnote, it is a fundamental material science constraint. The rare earth permanent magnet market is dominated by two systems, NdFeB and SmCo, which is samarium cobalt. Let's understand how they differ and why both matter. NdFeB accounts for approximately 90% of all permanent magnets by volume. Its energy product is 200 to 400 plus kilojoules per cubic meter. It operates at a maximum temperature of 150 to 220 degrees Celsius. Its corrosion resistance is poor. It needs a protective coating. Price ranges from $30 to $200 per kilogram. It is used in EVs, wind, consumer electronic, and industrial applications. The rare earth it needs are Nd, Pr, Dy, and Tb. SmCo accounts for 5 to 8% of the market by volume. This serves as a critical strategical node. SmCo accounts for 5 to 8% of the market by volume, but serves a strategically critical niche. Its energy product is lower, 150 to 240 kilojoules per cubic meter, but its maximum operating temperature is dramatically higher, 300 to 350 degrees Celsius. Corrosion resistance is excellent, no coating required. Price is much higher, 200 to 500 per kilogram. Applications are aerospace, defense, and high temperature industrial uses. The rare earth it requires is samarium. But here's an important wrinkle highlighted at the bottom of the slide. SmCo has a dual dependency. It requires samarium, which is China dominated, and cobalt, which is DRC dominated. So defense planners and analysts tracking SMCO supply chains must track two separate geopolitically exposed supply chains simultaneously. This dual dependency is frequently overlooked in the mainstream RE supply chain risk assessments. Now, we close chapter 1 with the three analytical questions that must be answered before forming any view on RE project or company. These questions are not optional, they are minimum starting point for rigorous analysis. Question 1. Which element, which stage, and which application? The phrase RE exposure is analytically empty. Cerium and Lanthanum dominate ore volumes but carry near zero commercial value. Neodymium and Praseodymium drive magnet demand. Dysprosium and Terbium determine whether a magnet functions in high temperature applications. You must always specify the element, the processing stage, and the end use before forming any view on project economics. Question 2. Where on the value chain does the company sit? A miner captures 5 to 15% of the final value. A separator captures more but requires rare technical skills that very few non Chinese operators possess. A magnet maker captures the majority of value but operates in a market 85 to 90% controlled by Chinese producers. The investment thesis must match the company's value chain position to its realistic access to downstream markets. The third question is that can a company monetize its whole ore basket? Most ore bodies producing large volumes of cerium and lanthanum alongside smaller volumes of the most valuable neodymium and praseodymium. Ce and La are often worth very little. Our project must either find credible buyers for its Ce and La and explain specifically who those buyers are, or accept that it is effectively subsidizing its NdPr production with volumes it cannot sell, which compresses margins and can make projects uneconomic even when spot prices are elevated. And finally, the closing thought of this chapter. Rare earths are not a commodity play, they are technology supply chain play. Most commodity sectors can be understood through price, volume, and grade. Rare earths require a layered understanding of chemistry, processing technology, geopolitics, and the specific technical requirements of end-use applications. A REE project is only as valuable as its ability to produce the right elements at the right processing stage and deliver them into markets that are currently 85 to 90% controlled by a single country. That is the analytical challenge and the opportunity of this sector. The three things to always track going forward: NdPr oxide and alloy prices as the commercial signal for magnet RE markets, dysprosium and terbium availability as the geopolitical pressure point for high performance applications, and processing stage versus China's share as a structural constraint on every ex-China supply chain story. Thank you. Hope you liked this presentation and do leave your feedbacks in the comments below.